For the last video of chapter 18, we're going to finish up with looking at more syntheses, right? We're just looking at a whole lot of reactions here. So for the last one, or rather this next reaction, we're going to look at condensation with hydroxylamines and hydrazines. You can see over here, we are introducing a couple new functional groups. We have hydrazine, which is this nitrogen to nitrogen species, and hydroxylamine, as the name kind of implies, is amine to alcohol functionality, right? So these are just two new functional groups that we're learning here. And for the reactivity, we've kind of already done this in class, so hopefully this looks familiar, right? Where with the hydroxylamine, right, for reasons we have already discussed, we know that the amine, right, is more reactive than the alcohol, right? Nitrogen is more nucleophilic than the oxygen, right? And so with a little bit of acid catalyst, which we can have as H+, right, or we can do HCl, H3O+, really anything, just some sort of acid catalyst, right? We end up with the following imine here, or rather this hydroxyl imine, right? Again, as discussed in class, right? For the other example, right, with the other functionality, right, there's no difference with which amine we're using, right? Because we have, for hydrogen here, we have NH2, NH2, doesn't matter which one attacks, right? And so, again, under these acid-catalyzed conditions, we form the following hydrazine-like group here. Right, hopefully both of these are pretty self-explanatory. Again, doing very similar mechanisms to the imine condensation, right? They're exactly the same, we just have, right, this different group kind of hanging off here at the end. For the next reaction, we're going to be looking at addition of alcohols. So this is very similar to the addition of H2O. Again, kind of like what we showed in class, we can attach things other than strictly H2O. So essentially, we're just doing the same exact mechanism, just this time we're doing it with alcohol. But one thing I will note, right, because if we're using alcohol, as shown here, right, ROH, which is any carbon group attached to the OH there, notice we end up with two ROHs at the end. Again, we're implying that ROH is in excess, right? The alcohol is in excess. So let's go ahead and take a look at that mechanism. Oh, and also, I should mention, right, the final product is called an acetal, which, right, notice there's no aldehydes there, even though al is at the end, so this is one of those things that are named kind of strangely, I guess. But an acetal here, right, see these two, they're almost protected alcohols, right? This is something that we call protecting groups, which we'll talk more about later in the semester, which allows us to essentially, right, we're protecting, in this case, protecting the alcohol. Right, so if something would happen where it would react with an alcohol, we can protect it instead to react somewhere else on the molecule. So anyway, let's look at that mechanism. So here, right, starting with that ketone, this could be an aldehyde too, right? The first step of the reaction is we're reacting it with the acid, right? Could be H3O+, could be HCl, whatever. We'll just denote it as a proton. Again, to make that carbonyl much more reactive, right? There's more of a pull on the electron density in that molecule, or in that carbonyl functionality. So now, we're going to go ahead and react with the alcohol. So in this case, we're just going to use methanol, okay? So we'll say R equals CH3. So we have CH3 here. So the alcohol is going to be the thing that attacks, right? This is going to break open our carbonyl, and we're going to get to the following intermediate, where we have OH, and then OCH3+. Right? Again, noticing our final product should be the acetal and not an alcohol. No alcohol is present in the acetal, right? So what's happening is, because there's just so much alcohol, right, in solution, there's going to be, if this is in excess, there's way more alcohol than our starting material, so the alcohol is just going to keep reacting until it's finished. So our OH here, we can have taking the hydrogen to get to our OH2 plus species, and then another equivalent of the alcohol is going to come through and remove water as our leaving group, right? And then we're essentially just doing the similar thing at the end here, where we need to deprotonate that OCH3, right? Because we have our alcohol, right, coming in, attacking that carbon center, so we can't lose that positive charge that we had in the previous intermediate, right? It still has to exist, so that's still there, right? And so for our last step, we can either have OH2 water, right, or another equivalent of alcohol come in and deprotonate our intermediate here. So it doesn't matter which one we use, but we'll just use water because that is present, right? We kicked off water as a leaving group, so we can go ahead and have water deprotonate to get to our final acetal. Right, CH3, CH3, and it doesn't really matter if you draw the line in between the oxygen and the CH3, right? But right now, this is the acetal, right? And this can happen in reverse too, right? So I'll leave that mechanism up to you, but the same reaction will happen in reverse. So essentially when we are saying that, right, we have a reversible reaction, right, like I've noted up here, it just means that if we did this reaction in reality, we'd probably have a mixture to some degree, right, of starting material and products. Okay. So for the last reaction here, this is a, wait, hold on. I've skipped something. Okay, that would have been bad. Okay, so to give you another example of a acetal here, we can do something, or form something called a cyclic hemiacetal, which is just a fancy name, or a fancy way to say that we can form an acetal sort of intramolecularly, right? You know that I love these intramolecular type reactions, where instead of having two separate alcohols, like we had before, right? Because remember in the last example, we had two equivalents of that methanol, or right, excess of methanol. Here, again, with an acid catalyst, we can use a totally combined alcohol. And the same exact thing's happening, so I'll leave that mechanism up to you. But we're just having both alcohols attach to the ring. Right, so instead of drawing them separately, they're just totally combined, right? So the two alcohols in question, I'll highlight in red, are here at the end. Again, losing water as before. And for the acid, right, we can use any acid, but in reality, we use, for these reactions in particular, we use something called taussic acid. Right, this TS group might look familiar from when we were talking about making alcohols a better leaving group. This taussic acid here is bulky, so it won't react, right? That conjugate base won't react with the reaction. It's a bulky acid, which we like, and also it's organic soluble, if I can spell organic right. It's organic soluble, meaning we can do this in organic solvent, which is nice. Okay, so to remove the acetal, right, because this is sort of, again, we're sort of, hemiacetals are kind of like you're protecting a carbonyl, right? Because notice, right, the carbonyl here is going to have much different reactivity than this whole hemiacetal business. So this is sort of a way we can protect a carbonyl, which we'll talk a little bit more about next chapter. But for any acetal, right, hemiacetal, any sort of acetal, we can reverse these conditions by using excess acid. So when we have this, right, we can just really take this product, or take this intermediate, really react it with acid, and we'll get back down to the carbonyl variant as shown here, I'll do a slightly different example, right? If we took this hemiacetal as shown above, again, did the same thing, HCl excess, doing the reaction with water as the solvent, we're going to get back to the corresponding carbonyl, right? Okay. So now for the last reaction here, we're going to be looking at something called a Wittig reaction. So notice how it's more of a pet peeve, right? But the name, right, is sort of German, right? So it's Wittig, not Wittig. So the actual reaction has been called a addition of phosphorus ylide. And a phosphorus ylide is this unique reactivity where the phosphorus is sort of this cationic species. And so the phosphorus ylide, hold on, I'm going to make one adjustment down below. This phosphorus ylide is this phosphorus species plus some sort of really electrophilic species whereby we react the phosphorus with that species to generate these SN2 conditions to generate this thing called a phosphorus ylide. Right? Notice the phosphorus is positively charged, right? It has to be. So this is something called a phosphonium salt. And then we react it with a species called N-butyllithium. NBU, right, and lithium. Right, remember this is sort of this cation, this will be this sort of cationic, or zwitterionic, species, where we have this really negatively charged carbon-based species. And what this does is going to deprotonate the hydrogen that's on CH3 or whatever we're using, right, to generate this thing called an ylide. Right, we have a lone pair on that carbon, so negatively charged, positively charged. So we're getting this really unique reactivity where the resonance structure for this can form right, and this is our ylide. Okay, so we get this real unique reactivity that can now react with carbonyls, and this is all born of the fact that, right, remember phosphorus is right below nitrogen, right, in the periodic table, right? Phosphorus in general is bigger, so it can expand its octet. So we can do these things, right, like where phosphorus, right, is more nucleophilic than nitrogen, right, based on those nucleophilicity rules we talked about, and also, right, it's bigger, right, it's in that third row, so we can expand its octet, right, because notice phosphorus down below has more than 8 electrons around it, right, it has 10 electrons, but it's fine with that, okay, because it's a bigger atom, it has those d orbitals to expand its octet. Okay, so the actual reaction itself, right, notice down below here, I have the reaction drawn. I had included the positive charge because it was missing before, right, so we have this species here, right, we're reacting with N-butyllithium, and we're reacting with the carbonyl, and we get to the following compound, this alkene here. Right, I'm not just missing the oxygen, it's a different species, where the carbon, the end of that alkene, is the carbon here. So let's take a look at that mechanism and see what we get. And it's less complicated than it seems, I promise. It's a unique mechanism, but it's not particularly steppy. So we have our carbonyl, right? And we make our ylide, just like I showed above, right? Where we have this as our reactive species. Right, we have our phosphorus and we have our carbanion. And what it's going to do, it's going to react like this. The nucleophile will attack the electrophile, and the double bond here, the carbonyl to that carbonyl bond, that instead of breaking up onto the oxygen, it's going to actually attack the phosphorus. Right, so following our electrons here, we get to the following intermediate. We get to the cyclic species here. Oops, CH3, or sorry, CH2. Right, so we're forming these new bonds here, right? So this is called the oxaphosphatane intermediate. Okay, this really unique cyclic species. Notice, right, it's very sterically strained, right? It does not want to exist like that. Kind of like these tetrahedral intermediates we talked about, right? When we're dealing with esters and acid chlorides, this is going to want to condense back down. But it's going to want to condense back down in a way that it prefers to, okay? So it actually, instead of breaking down to get back to our starting material, it's going to break down like this, where we have this sort of shifting of electrons occur like this. Okay, so again, just following the electrons, we get to the alkene species that we have shown as our product. Right, just like this, where we have, right, this is our alkene, right, that methyl group from before that was on the original carbonyl, right, that has not changed location, right, that methyl group is still here, has not done anything. And then we form this as a side product, right, this oxidized phosphine. So this is triphenylphosphine, triphenylphosphine oxide. This is a really stable species, right? The phosphorus kind of likes existing like this, more so than it does the illid, okay? The illid is really reactive, and the intermediate, that oxaphosphatane, would rather become the alkene rather than go back to its starting materials, okay? So this is transformation, right? Not very steppy, but we have to kind of make sure, right, we're doing this sort of, right, atom shuffle here appropriately, right? Where we have the groups connect together, right, they connect in one way, and they come apart in another. And we can do this with any sort of system we want to, right? So for another example that I'll show down below, we can have any sort of carbonyl, any sort of phosphine that we like. We need to make sure we're combining it with a good base, right, this N-butyllithium, so we can generate the illid, okay? So we're generating the illid over the course of the reaction to get to the final product. And essentially all we're doing, and the sort of theme of these reactions, oops, that's not what I want to do. Theme of these reactions, we're just exchanging the oxygen for all these carbons here. So if nothing else, right, all I have to do is look at the carbonyl, right, and say, okay, the carbon is staying the same, but we're going to be losing the oxygen and replacing it with any carbons on the phosphorus species. Right, you see that? We're just replacing the oxygen with the carbons. And in class we'll get used to looking at these sort of reactions here. But another way we can also draw these illids, right, is instead of doing the N-butyllithium thing, we can do that too, right? But we can really start anywhere. We can start with whatever phosphorus species we want with the alkyl halide to get to the phosphonium salt, then add the N-butyllithium. Or we can start right from the alkene. Right, we can have this alkene here replacing things above the reaction arrow. So we'll get used to looking at these things in a slightly different way too, and we'll get more practice with doing these illids. But this is a really great way, before we end here, of going from carbonyls, right, ketones and aldehydes, to alkenes, okay? That's the real goal here. We're going from carbonyls to alkenes. Okay, so in class, we'll look at more examples of these, okay, and the rest of the chapter as well.